Hi, everyone. Welcome to the All of Us Friday office hours. My name is Caitlin Rantala. I'm a senior communication specialist here with the DRC, and I will be your host for today's session. Today's presentation is led by Victor Borza, who will lead a discussion on the computational strategic recruitment, representation, and coverage studied in the All of Us research program. Today's presentation will be recorded and posted to our YouTube channel in the coming weeks. Before we get started, we have a couple of announcements. The Healthy Americas Foundation has an upcoming funding opportunity. You can scan the QR code for more information, and I'll give everyone a minute to scan that code now. And we have one more announcement because there is another upcoming funded training opportunity with Aim Ahead, and I'll give everyone a second to scan that QR code now. And that leads us to today's speaker. Victor Borza is a dual degree MD PhD student in the Department of Biomedical Informatics at Vanderbilt University's School of Medicine. His research includes methods for improving representativeness in large biomedical data sets, the relationship between dataset composition and downstream algorithmic performance and fairness, and the subphenotyping and prediction of outcomes for people living with obstructive sleep apnea using electronic health data records. Victor received an AB and Bachelor's of Engineering degrees in the Biomedical Engineering from Dartmouth College in 2018, joined the Vanderbilt MD PhD program in 2019, and received an MS in Biomedical Informatics from Vanderbilt in 2024. He is funded by an F30 Graduate Research Fellowship from the National Heart, Lung, and Blood Institute, and received the 2024 Martin Epstein First Place Student Paper Award from the American Medical Informatics Association. And with that, I will turn the screen over to Victor, and he can share his slides.
All right. Thanks for the introduction, and thanks to the All of Us team for inviting me to talk a little bit about my work. As it's already mentioned, my name is Victor, and my paper is called Computational Strategic Recruitment for Representation and Coverage, studied in the All of Us research program. So I wanted to start first by just talking about representation and representativeness in the ways that our group has defined it for this paper, just because there's a lot of definitions out there. But representation is the idea that a research cohort should reflect the attributes of interest of the population that it studies. And representativeness is a quantification of representation, often measured through some sort of statistical distance measure. I'm not going to go too deep in the math during this talk, but you can find it all in the paper if you're interested. At a high level, imagine that you have a target population and it's comprised of green, blue, and orange individuals. You could then imagine that you could take two cohorts from this population, cohort A and cohort B. Cohort A is entirely composed of green individuals, so we might consider this a non-representative cohort, where the green is overrepresented and blue and orange are underrepresented. On the other hand, we have cohort B, which we might consider representative because it includes all the different groups from the target population, as a simplified example. However, it gets a little bit more nuanced than that. Representation is an incomplete measure. The motivating example here is imagine you have a population, which is this right-hand sided graph that is composed of 1/2 green individuals, 1/3 blue, and 1/6 orange. If you were to take a fully representative cohort, call it cohort 1, it exactly reflects those population distribution among those groups. But that's not the whole story. You might want to consider then, well, maybe you want a cohort that equalizes all the groups, something like cohort 2, which we call covering. And we define perfect coverage as the idea that a research cohort should include equal proportion of all groups of interest. It's important to note that depending on the scientific analysis that you're planning on doing, you could want a cohort that's more representative or a cohort that's more covering. Some high-level examples might be a representative cohort might get you associations that are closer to the true value in the population, whereas a covering cohort might give you more statistical power if you're looking at differences between groups. It's also important to note that these two goals can be in tension sometimes. If you just look at the graph, you can see the proportion of green individuals and orange individuals is necessarily going to differ. And we see a similar pattern, though at a much greater scale, when we compare something like US population demographics from something like the census against balancing all the different group proportions equally. So setting some value between representation and coverage is really important if you're trying to build a large-scale biomedical data set that might be interested in many, many different types of scientific questions. I also wanted to briefly show another analogy that this isn't just true, in this biomedical research field, but an example uh, in the civics field is to compare the U.S. House of Representatives and the U.S. Senate. And this holds true for many sorts of bicameral legislatures worldwide. But in the U.S. House of Representatives, each state is allocated a number of representatives that's proportional to that state's population. So states with more people living in them get more representatives. On the other hand, the US Senate has two senators from every state. So we might think of the House of Representatives as being a representative set, whereas the US Senate might be more of a covering set. And in US policy, they have the luxury, I guess, of laws having to pass through both houses. But if you're working with one data set or one large program, you kind of have to find a balance between the two. So, talking about why we care about ideas of representation and coverage, I like to think of just a few examples of this on this spectrum, from the left-hand side of ethical and social reasons to the right-hand side of thinking of scientific reasons. But this is just a small subset of the reasons you might care, and this is just one way of thinking about it. But on the left-hand side, we really draw a lot of ethical inspiration for these concepts from the Belmont Report, which I'm sure everybody here is familiar with from all of us training. But it's really been a guiding statement that has guided the way we think about biomedical research ethics in the United States for decades. And specifically, one of its components is this principle of justice, which specifically calls out in the Belmont Report equal participation in studies, which allows then for the equal distribution of benefits to the different participants. On the right-hand side, we can also think of scientific reasons, and it's been shown that data sets that aren't representative have skewed associations, have values that differ in their magnitude. And the example that the authors talk about is thinking of representation in the data set through this collider effect. If you're interested in finding the link between an exposure A and an outcome B, well, it's possible that both of those have some link to R, the representation in the data set, whether somebody is in the data set or not. And that is sort of a collider effect that you cannot really control for because your entire data set is marked by that effect. And that can cause some skewed associations. At the confluence of the ethical, social reasons and the scientific reasons, we have ideas of perpetuated differences in performance. It's been shown in many different studies that groups that have been underrepresented in data sets, then when models, for instance, are built on those data sets, those models don't perform well for the groups that are underrepresented. And this isn't a universal truth. It doesn't always work exactly in that way, but it has been shown numerous times that that is an observable effect. And that's particularly important for translational research because our research hopefully eventually gets put into clinical practice. So making sure that we're not perpetuating disparities in performance or differences in performance from different groups when we study it to when we apply it in the clinic. So representation and coverage are also baked into the core value statement of all of us, even though they don't necessarily use exactly those words. But just quoting from the website, the first two core values, the first one being that participation is open to all, and the second one being that participants reflect the rich diversity of the United States, which align with the similar goals of having a data set that is reflective and one that also reflects all the different groups and it's really open to everybody. It was formalized in 2019. I believe this was from Josh Denny's paper. He specifically and his team had goals of 75% of participants coming from groups that had historically been underrepresented in biomedical research, and specifically 45% from racial ethnic minority groups. So these were putting just some numbers to it. Um, and I also want to stress that these ideas aren't new. They're not just, I'm not the only one working in this space. Methods for improving representation and coverage in cohorts have been studied in a bunch of different aspects, some within the biomedical space and some outside that space more broadly in the computer science space, as well as in niche cases like hiring or selecting citizens' assemblies. The way I like to think about this distinction of sampling and recruitment is whether or not you can select records or select participants based on their attributes. If you can, you're in this, what I term a sampling regime, and if you're not, you're kind of in this recruitment regime. And I've just linked a bunch of different sources. The ones in red are some of my previous works in both of these areas, and the ones in black are other people's works. I just wanted to emphasize that other people have also been thinking about this problem. And specifically, I also wanted to call out the MIDRIC group because they, not necessarily in the sampling space, but they had been thinking of using very similar statistical distance measures for data sets of COVID-19. And it was like, it aligned really closely with like the timeline that I was working on these things in parallel. So to wrap up the introduction part of this talk, I just wanted to emphasize that my study goal was not to be a retrospective analysis. It wasn't just to like look back and see what all of us had done and just say like, okay, that's it, that's the state of things. It was rather a prospective or almost a counterfactual analysis, like what could have happened under the same overarching constraints, but if resources had been prioritized in a different way. And we can also think about it as if you're starting up a new program and you have the option to align your recruitment resources in a certain way, what would the final cohort look like? Or if you're in the middle of recruitment and want to potentially shift your the demographics of those of that cohort, how would you go about achieving a shift in the direction that you want? So I want to quickly pause and see if anyone has any questions so far. Okay, I will move to some of the methodology. So starting with data sources and the way I achieved harmonization. So so aligning all of us with just the US population at a broad scale, I used census data, and I used specifically version CCS 2022 all, which is from the American Community Survey. A it's not a full census in the way that the decennial, like the 2010 or 2020 censuses are, but it's supposed to be an update and it's still conducted by the US Census Bureau. It's built off of numbers from the 2020 census, and it's just supposed to be a little bit more temporally accurate. And the reason this is important is because this data set, I believe those numbers were up to date as of July 2022, which happened to align really well with the All of Us data version that was available at the time I started this analysis, C 2022 Q4 R9 or V7. And that one, I believe, had recruitment dates up until the end of June 2022. So having the temporal alignment was really helpful. Age is reported similarly. The census data is binned into groups of 5 years, for instance, like 0 to 4, 5 to 9, et cetera, whereas All of Us gives dates of birth for participants, but notably it's for adults only. Sex and gender, the census data reports it as sex and specifically casts it to either be male or female. But based on the way that they ask the question, we chose to align it with gender in the All of Us data set rather than sex assigned at birth. And that has to do with how the Census Bureau asked this question. Similarly, there are differences in the races reported by the two different data sets. The notable ones being that the census data included individuals in this bin of American Indian / Alaska Native, which at the time of the analysis was not available in All of Us. I know that's changed since. And then similarly, or conversely, All of Us data had individuals who identified as Middle Eastern North African, which was not available in the census data at that time. I believe that was a change that was going to come with the 2030 census, and we'll see if that holds true. Ethnicity was similarly reported in the two data sets, and location. The census data uses FIPS codes, which correspond to counties, whereas the All of Us data in the control tier gives 3-digit zip code or zip3. These are able to be aligned through some lookup tables from like the US Postal Service. And finally, and this is an important point, is on imputation. So the census data in this specific table that had the most granularity, they enforce imputation. And what this means is if somebody selects, for instance, some other race or doesn't fill out the question, the Census Bureau goes in and backfills that value with their kind of best guess of what it would be in order to fill out the table. And they detail the way that they do this process. Now, they've got access to a little bit more advanced or a little bit more granular data than we do. And all of us, for instance, they can look at household members and see what they put when they're doing this imputation process. Notably, all of us data doesn't do this imputation process. If somebody skips a question or puts some other value, like the box that just says some other value, it'll be reported as such. But in order to harmonize the two data sets, I had to apply the same imputation process that the census data used onto the all of us data set. And in the sensitivity analyses, of the actual paper, I tested a bunch of different imputations to see if that really impacts the overall results. And while it does change the numbers a little bit, it doesn't meaningfully impact the overall results that we see. Starting with that retrospective part of the analysis, what I'd found is that all of us is more representative and covering than most similarly sized and scoped data sets. And I think Brandy Mapes actually had like a paper back in 2020 that compared it specifically to other data sets of similar size and scale. I'm showing here just the actual all of us results over time. So in each of these charts, the x-axis indicates time of recruitment, while the y-axis indicates percentages for these various groups. All of these groups would be considered underrepresented in biomedical research by the definition that the program uses. Their census levels are these thin, sort of lighter colored flat lines in each panel, whereas the all of us participant percentage over time is indicated in these sort of darker, thicker lines. And what we can see is that in almost every group, the all of us proportion of these groups was at or above the census level of proportion of these groups. So indicating that they're really aligned with the goals of representation and coverage. The one example that doesn't quite follow this trend is participants who identify as Asian race. And we can see that they're uh, represented at a lower percentage in the data set relative to the census. So going into our methodology and how we did everything, I've got a little flow chart that I wanted to walk through. We start with some expectations of recruitment site distributions. So various sites, maybe we know this ahead of time. This is particularly true if you've already done some recruitment activity and are just looking to change the strategy going forward. You might have an idea of what the different population distributions look like. Or if you're starting a project from scratch, you might not know. So I have this kind of like gradient, hazy line to indicate that. In our experiments, we kind of assume this worst case, that you don't know, and you can just put something called an uninformed prior, an uninformed Bayesian prior onto it and say, well, we don't know, but we're going to let the model learn over time. So starting with these distributions, we then look at the target populations. So in this case, the top pie chart might indicate what the census population looks like, and the bottom one might indicate what a perfectly covering cohort would look like that equalizes group proportions. We put these two targets, as well as the expectations of recruitment site distributions, into an optimizer. I'm not going to go through all the math that it uses, but basically it balances the two objectives and it tries to minimize the distance between the predicted recruitments and the two goals. And what the optimizer spits out is something called a policy. It says how much, if we have a fixed budget of recruitment resources at any given step, how should we allocate it among the available sites in order to achieve the goal distribution or get as close as we can. So let's say, for instance, this is the policy that it spits out. Then in real life, you could go and actually recruit participants according to that policy. In our experiments, we simulate this recruitment. So we assign, these proportions of the total recruitment budget to each site and say, okay, under these conditions, how many participants would we get and what do they look like? So that becomes this next step. So the cohort participants are added to the cohort in simulated recruitment, and we get a better idea of what each site's distribution looks like. And this is a really key part of the whole cycle that makes the method sort of strategic or adaptive even, is that the more you recruit at different sites, the better and better you learn about the participant distributions at all of those sites. And that means that your optimizations then become more and more accurate and are able to get you closer and closer to the target. And this is an iterative process, just like real world recruitment. It's done over time and it's done in steps. We used in our analyses sort of this 3-month update in the main results, and then a 1-year update in the supplemental results. And both showed a substantial improvement, though, of course, the more frequent update scheme allowed for better policies because there's more of these updating steps involved. So jumping into the recruitment site distributions and what would that look like for a program like All of Us? So there's 2 ways that we formalized it. The main body results of the paper split into the electronic health record or EHR sites. Because All of Us recruits all across the US, we can think of it as a network of recruitment sites that could be prioritized, e.g. through funding. And the way that we found this site data is actually for all of the, I believe that any of the tables that originate from the EHR, something like observation or measurement, we use the observation table here. You can find a corresponding observation underscore ext table, and that has this value of src underscore ID or source ID. It links to a 3-digit site code. And this has actually been used by others, including our co-author, Lena Suleiman, for other analyses looking at differences in EHR data between sites. But there are 50 of these EHR sites, and I'm not going to go through everything. I know the text is probably really small and hard to read. You can see the whole table in the paper if you're interested. But I just looked at, for each site, what are the most common zip3? So what are the most common geographic locations of participants coming from that site? And then what, what's the closest big city kind of, or what's the closest, broadest region nearby? And it highlights that these sites are all across the United States, which uh, substantiates the program's geographic diversity in that sense. We also looked at, so further substantiating that claim of geographic diversity, we also thought about geographic sites using that zip3 level information. And we ran a whole parallel analysis also in the supplement, assuming that you could allocate sites or allocate resources to recruitment sites based on their geography, rather than just saying the EHR site codes. And this, again, it really highlights that all of us participants come from all over the United States. Now, there's certain concentrations, of course. We see some, for instance, in large cities like Chicago or Boston or Philadelphia as well. But all of us has a fairly broad reach. The reason we chose to use the EHR site-based analysis for the main results is because it links a little bit better to our overarching model that we apply, where we're saying, okay, here's how we can allocate resources to different sites. It might be a little bit harder to think about what that might mean for geographic regions, but assuming that you could, we also ran the results for this. So any questions at this point? So there was a question in the chat, why do some sites have very different locations? Yeah, so that's most of them. I'll see if I can go back to it really quickly. Yeah, so I think you might be talking about site 638, which has locations in 3 different states, versus others. I think what's happening in those cases is probably it's like one large medical center that happens to have different locations or different sub-hospitals, but it's all coded within the same medical center. Most of them tend to be geographically quite close to each other, but I think site 638 was one sort of exception we saw to that. Hope that answers your question. Any other questions? Cool. So going a little bit into the experimental results. So if we imagine, so looking at the policy that we have, what is the actual resource allocation that we get to different sites? And what we found is that the optimal policy shares similarities and differences with the program's historical policy. And the way we map this, I'm just going to go over the axes really quick, is each of the 50 EHR sites are listed on the x-axis, and the number of participants recruited in like whole numbers is listed on the y-axis, log scale, because there can be pretty big differences between different sites. And in this graph, the red dots indicate how many recruitments actually occurred at that site, whereas the blue violin plots indicate how many recruitments would have been allocated to that site under the different experimental runs. This is specifically showing data for 40 different runs, which gets you the range that you see in the violin plots. And I think this coloration makes it a little bit easier to see. The similarities are coded in purple, and more than half the sites, notably, have the simulated recruitment amount of those sites overlaps with the number of actual recruitments that occurred there. There are notably some sites that are more prioritized by our model. Those are highlighted in blue, and sites that were less prioritized by our model relative to their actual amounts, and those are listed in red. But again, a lot of the sites, we see overlap in the actual number of recruitments to how much would have been assigned to that site in simulation. So looking at what the outcome of this policy is, what do the actual cohorts look like that end up being recruited in simulation? So in simulation, one of our main results is we find that we can recruit a more representative and covering cohort under the assumptions that we apply. And what this graph shows is iteration. So I talked about 3-month update cycles. We call this quarterly. So we're basically showing time on this x-axis. And then on the y-axis, I'm showing representativeness on the left-hand side and coverage on the right-hand side. It's worth noting that these map something called Kullback-Leibler divergence, or KLD. The main takeaway here being that a lower divergence or a lower distance is considered more representative or more covering. And in both graphs, the dashed lines indicate the historic progress of the program, whereas the solid lines indicate the experimental simulation values. And it's kind of hard to see, but there is a confidence interval, which is that shaded region around the simulated results that averages across those 40 experiments. And what we find is after about the fourth quarter, so after about 1 year, we're seeing the simulated results having both better population representativeness and coverage than we saw in the historical baseline. And the other key result that we see here is that in the historical results, it seems like, at first it starts getting very population representative and then shifts towards prioritizing coverage and not so much with representation. And then it almost seems to flip back and you see the line go down so getting more population representative and a little bit less covering over time. In simulation, we find that the lines generally track with each other and that they both tend to decrease pretty stably over time. So in a way, it's finding a different equilibrium that's able to achieve both population representativeness and coverage. So these are all kind of abstract values, and KLD, or Kullback-Leibler divergence, can be kind of hard to interpret sometimes in terms of what that actually means and what those differences are. So I wanted to make those results a little bit more evident and a little bit more real. And the way I do this is I look at particular groups and I see, what happens under our simulation results compared to the actual historical results of the proportions of all these different groups. So in this case, all the groups are listed on the x-axis. We have age, gender, ethnicity, and race. And then the proportion that those groups comprise of the cohort is listed on the y-axis. So if we look at the actual results, we see that there's some baselines. The dashed line indicates a perfectly uniform group proportion. This corresponds to a perfectly covering cohort that balances the proportions of all of the different groups and equalizes them. The stair-stepped solid black line indicates the census proportions of all these different groups, and it changes expectedly for all the different demographic groups. But using these two values, we can then define three regions. We can define this blue overrepresented region as indicating values that are above both the coverage and census levels. We can define this red underrepresented region to indicate that a group is comprises less than either its representative or covering values. And we can define this target zone in purple, indicating a group is somewhere between its census levels and the covering levels. And we want to be in that purple zone if we're trying to target a balance between representativeness and coverage. And I know there's a lot of different dots and violin plots shown here. The black dots indicate the All of Us final actual cohort, and the green violin plots indicate the simulated cohorts. And a few that I just wanted to highlight that showed really an area of potential improvement that this strategic recruitment had was specifically looking in the non-Hispanic, Latino, Asian identifying participants at all genders and all ages. And what we see is that these groups seem to be underrepresented, and that aligns with the graph I showed many slides ago that looked at the proportion of Asian identifying individuals in the data set. And what we could see is in simulation, these numbers can be pretty substantially increased across the board. And some of them can even be brought up from this underrepresented zone up into the target zone. So it really shows a highlight of making it practical. Where could there be potential improvements using this strategic recruitment process? So that then begs the next question of why are we seeing these improvements? And this made up the discussion section or the majority of the discussion section of the paper. And basically, there's no clear answer, and it's likely going to be multifactorial. The first option is really just that all of us used a different objective function than we did in where to prioritize recruitment and open new sites. And they just, used some other measure that they were trying to optimize to. And similarly, relatedly, that all of us didn't allocate recruitment resources to optimize representation and coverage as we defined it. Because if they have a different set of goals, it will be optimal to them, but not necessarily to us. Another really key component is if our simulations and assumptions just don't necessarily hold true. There are some really fundamental assumptions to this work that might not hold true in reality. The first one being that recruitment is unlikely to be interchangeable between sites. We assumed at the outset that participant numbers, that a participant from one site is equal to a participant from another site, that their site didn't matter. And we can imagine that's very easily not true, that in certain regions, the cost of acquiring a new participant might be a lot higher than others, and especially in sparsely populated regions, it might be a lot harder. So that's a factor to keep in mind. We just didn't have per site cost data available to run that sort of analysis. I think that would be a really cool potential analysis to run. The second assumption that might not hold true from simulation is the funding cycles that we applied. So we used the quarterly, which is a 3-month cycle, or annual, which is a 12-month funding cycle. That's a really short time frame. They did draw some inspiration from other NIH funding mechanisms. For instance, annual updates and annual project reports are pretty common in most types of grants. 3 months is a lot faster. That it might be more in line with certain types of OTA or other transaction and awards, but might be less common for traditional NIH grants. And at any rate, being able to reallocate the funding resources so commonly is not necessarily always going to be practical. And the third and key limitation of the simulation is that we assume that the response distribution is a fixed quantity at each site, and that we can get better and better at modeling it, but that it doesn't drift over time or drift in response to the amount of recruitment that occurs there. Substantial additional recruitment may change this response distribution. You can imagine that this would be particularly true if you have a site that has a very, intentional recruitment process, and who they are recruiting as participants might be very different than the geographic region and who would come to the center at baseline. So those efforts might not scale up the same way as at other sites because the investment sort of has shifted the response distribution at that site from its, let's say, geographic baseline. Nevertheless, I think there are still some key contributions, and it really has to do with the way of framing this work and what it and it's proposing like a new way to think about the way that we assign recruitment resources and the way that we go about recruitment. So the key contributions are formalizing the study cohort goals of being representative and covering simultaneously. I think it helps because it gives a little bit more directionality than not to say that there's like anything wrong with setting goals of, for instance, the 75% from underrepresented groups or the 45% from racial and ethnic minorities groups, but that's not, it's kind of a little bit vague about how you want to achieve that. And using values like being representative or covering is just more concrete and saying, well, what distribution do we actually want to achieve with our overall population? The second key contribution is developing a computational method or a computable method for prioritizing how recruitment resources are allocated, letting it be a quantity that you can optimize and think about and try to achieve whatever your demographic goals are. And the third one is really is a proof of concept evaluation in a large national data set. And I think all of us was really like an ideal test testing grounds for this kind of analysis because it has national reach, it has hundreds of thousands of participants, and you know, across a large number of sites. And it provides a historical baseline because I've had done some previous work sort of developing the foundational methodology of this idea of adaptive recruitment. But in those analyses, we were really limited to saying these are the sites, but we don't know what the actual recruitment policy would look like. So we were limited to comparing, you know, let's say if we equally distribute resources to every site versus if we used our strategic or adaptive method. And I think what all of us provided in this analysis is a really good baseline of a program that is intentionally tried to achieve goals aligned with representation and coverage and gave a historical baseline that we could compare to. So I just wanted to give some acknowledgments. First of all, to all of my co-authors who are shown on the right-hand side, and especially to my advisor, Dr. Bradley Mallon. Also want to acknowledge all the feedback from members of the DRC who saw a version of this presentation back in January and gave me some really good feedback and some really good thoughts, especially, you know, contextualizing the results. Um, of course, want to thank all of us participants as well as the program more broadly for allowing this research to occur. And I wanted to thank, of course, the funding agencies that have supported this work.